Let's take a look at the last section in our notes for chapter 12. It starts with the collision model. According to the collision model, molecules must collide in order to react. But the frequency of collisions in a reaction is often much higher than the rate of the reaction. So collisions aren't always successful. Just because molecules are colliding does not necessarily mean they are reacting. The collision model accounts for this by saying molecules need not only collide, but they must collide with sufficient energy to break the bonds of reactants and appropriate orientation, also referred to as sterics. So these are kind of the last two concepts that we need to cover to end this chapter. So we did a POGIL worksheet on temperature and molecule movement. Well, here we have a diagram showing us how molecules at higher temperatures are more likely to collide with the minimum energy, sufficient energy needed to break those bonds and react. So hopefully from that POGIL, we could see that A, temperature is average kinetic energy, and B, when we increase the temperature on a reaction, we increase the average kinetic energy. Kinetic energy is 1/2 m times v squared, mass times velocity squared. So we're not really increasing the mass when we increase the temperature. We're probably increasing the velocity, right? So we're making the particles move faster, and therefore when they collide, they're more likely to have a successful collision that has enough energy to promote a reaction. This graph shows us the same thing, the same concept, maybe just in a slightly different way. Let's practice graph reading. So on the x-axis, we have energy. On the y-axis, we have number of collisions. T2 and T1, one of those is representing a lower temperature and one is representing a higher temperature. Can you look at this graph and tell which temperature is representing a lower temperature? T1 is a lower temperature and T2 is a higher temperature. We know that because while both curves have the same area underneath, T2 has spread out. The curve has shifted more towards the right side. It includes more particles, more collisions with a high enough energy to prompt and promote the reaction. So we can kind of see that under the first T1, only this many particles have a relatively low energy, and just a few particles, only in this purple area, have a high enough energy to surpass this thing called EA, which we're going to talk about in a minute. EA stands for energy of activation. So enough energy to get started, to get the reaction started. However, if we look at T2, where the distribution of energy has been spread out, right, we get this shape of curve. The total number of collisions between particles, right, that surpass the activation energy actually is larger. Can you see the area under the T2 curve is larger at this high energy region of the scale? So by increasing temperature, we have provided sufficient energy to break the bonds of reactants for more of the molecules that are reacting. So by increasing temperature, it does not guarantee that every collision will have sufficient energy, but it increases the likelihood that more collisions will have sufficient energy because more particles are moving at a higher speed and will have higher collision interactions with one another. Now, I want to talk a little bit about energy of activation, this symbol here. and I didn't make a nice enough room on this part of the graph. So please add just one page to the bottom of your notes, and we're going to talk a little bit about energy of activation. You're probably going to need to draw, maybe pause the video and draw these two graphs, and we'll talk through them because they help us explain energy of activation, what it is and why it's important. Hopefully you've seen a graph like this before. Let's practice reading them. The graph on the left shows the progress of the reaction on the x-axis and the amount of energy on the y-axis. The curve that you can read in black starts with the reactance AB, and then the curve increases on the energy axis, right? It has this peak, and then it falls, and then it ends with the products CD. So one of the things I want you to notice about this graph is that the amount of energy that is contained within the reactants A plus B is higher than the amount of energy that is contained within the products CD. There is more energy contained in the reaction vessel at the beginning than at the end. What happened to the excess energy? We know it cannot be created nor destroyed. That excess energy must have left the reaction vessel. It has escaped. It's been passed on, perhaps to the environment, perhaps as heat. So the energy that was lost makes this an exothermic reaction. So it is labeled exothermic because remember the prefix exo meaning out, thermic, heat energy. So there's been an overall transfer of heat energy out of this reaction. We also sort of notate that with this symbol here, the negative delta H. Remember, delta H is change in enthalpy. Change in enthalpy. Enthalpy is essentially total heat energy. So there's a decline in the total heat energy of the system because some energy has exited or left the system. And we know that because there is a lower number of energy, a lower height on the energy curve for the products than the reactants. So that's something that you probably already knew about a graph like this. The only thing we're adding is a description of this hump. The hump that exists between the reactants and the products. It is labeled here with an EA symbol, and you can see that the distance from the starting point of the reaction to the height of this peak represents the amount of energy that must be overcome in order to get the reaction started. You can think of it like a spark, right? In order to start a fire, we need a small spark. Even though any sort of combustion is an exothermic reaction, fires burn for many days, weeks, months, but in order to get it started, there still requires some energy input. Physically, you can think of it as rolling a ball up a hill. If you are capable of rolling a ball to the top of a hill, then when you release that ball, it may release a lot of energy depending on how far it can fall. But first, that sort of potential energy has to be put in. So that is another way to think about it. So the graph on the left represents an exothermic energy exchange, right? Where the reactants have less energy than the products. And they have added some definitions to the bottom here. We have our definition for activation energy, the minimum amount of energy required for the specific reaction. And then just some notes about this graph. The reactants, you can see AB are higher on the graph than CD. That means it's exothermic. Also, another way to think about it being exothermic is that the energy of activation for the forward reaction is less than it would be if you tried to force the reverse reaction. In the reverse direction, if you tried to take C and D and turn them into A and B, you would have to overcome a larger energy obstacle. You'd have to push the ball up a taller hill and less would come out. So if the forward reaction activation energy is less than the reverse reaction activation energy, that is another way of thinking about the definition of exothermic now that we're looking at these graphs. So graphs like these are really what we want to be able to use to help us understand the definition of activation energy. Whenever it comes up, we often see graphs like this to try to describe it. You might be given a graph like this and asked to identify which portion of the graph represents the activation energy for the forward reaction, for the reverse reaction, or is this graph generally endothermic or exothermic? If we look at the graph on the right, we can see an endothermic representation. We know it is endothermic because the amount of energy for the starting reactants is less than that of the products. So just reading right over to this energy scale, this number here represents a lower number than this number here. So energy is being added to the system, it's being stored in the products. This happens when a plant that has made monomers, small sugars of glucose, links them together into polymers, long chains of glucose. And by continually linking these small energy molecules, they make large complex energy molecules. This is a way to store energy longer term. And so simple sugars like glucose become things like starch in endothermic reactions. So some energy is required to link those together, but there's a benefit in doing so. The energy is stored for later use or later needs. We can still see those same features from the previous graph. This time we have a positive delta H because positive means the change in energy required an input, endo for in. And we can also see the activation energy for the forward reaction and the reverse reaction labeled here. So when we kind of step back up to the last section of the notes on catalysts, this really comes in handy because a catalyst, by definition, speeds up a reaction without participating in it. Remember, catalysts are there first on the reactant side and then on the product side when we look at a reaction mechanism. Also, catalysts usually work by helping molecules collide with the correct orientation, sterics. So the other thing that is needed in the collision model, besides accurate speed of particles, is accurate orientation. And that's what the catalysts often do. They hold or position the particles in the most useful way so that when that collision occurs, the two atoms that need to bond together actually strike one another in a useful and productive way. So sometimes we have diagrams where you might have a chemical reaction between carbon dioxide, and these are actual particles, carbon dioxide, and water. And what we're looking for is carbonic acid. So let's say we are combining carbon dioxide and water to make carbonic acid. What would be the best orientation? What would be the best positioning for these two molecules to interact with one another so that they can form something where one OH combines with an oxygen on one side and one OH combines with an oxygen on another side? So that catalyst might help hold one molecule in position so that the next molecule can approach at the right angle rather than approaching at an angle that's less useful. It can approach at an angle that's more useful to achieve the desired outcome. Finally, we have something called the Arrhenius equation or Arrhenius. I've heard it pronounced both ways. Arrhenius is a scientist who wrote an equation that quantified this whole model. And the cool thing about it is that he writes it here in terms of K. Now, we've been using this constant K, but not really talking about what it represents. And now this equation tells us what it represents. K represents the following. A, something called the frequency factor, which takes into account collisions and orientations. That doesn't come up very often, but then check this out. K also represents the inverse natural log, right? The opposite of the natural log, raised to the activation energy over the universal gas constant. Yeah, this research was done for gases, right? The universal gas constant and temperature. So that's pretty cool. A lot of K, the constant, a lot of what's being held constant is actually temperature and activation energy, which is the presence or absence of a catalyst. So all this time I've been wondering what K was. That is what it is. Y equals the temperature and presence or absence of a catalyst times the concentration to the N. That's the rate law we've been using. So that's kind of exciting. It just explains what's really baked into that K. And if we look more closely, what we'll see is that we have a negative exponent here, which means that it's in the denominator, and temperature, therefore, is a very big factor because it's in the denominator of the denominator. So it's kind of in the numerator. So we know that when you increase temperature, of course, you increase K and therefore the rate of the reaction. And when you decrease the activation energy, then you increase K or the rate of the reaction. Both of these things increase the rate of the reaction. So that's the mathematical logic behind K that Arrhenius was able to put together. That's pretty cool. We already knew some of that, but we're seeing it just written as a mathematical expression. We don't really use this equation to do any calculations in class, but I'll show you something cool that we can do with it, even though it doesn't really come up very often, like on the test. So in this format, the equation has limited usefulness, but in a different format that you can see right here, we have the straight line version of the equation just by logging it. And so we end up being able to plot y versus x, right, the log of k and 1 over time, and we can solve for activation energy, right, because r is a constant. So that's pretty easy to do. So that's kind of exciting. So we can find how much energy it takes to get a reaction started. And I did one of these here with this data set. So we were given temperature and we were given K. And I used kind of a Google sheet here to take those numbers. And as you can see, I took the temperature in Celsius, turned it into Kelvin, took the inverse of that temperature, right, in Kelvin, and then took the K values and logged them, and then found the slope of that y versus x, the slope of the log of K over the inverse of temperature. And that's equal to 1. That slope is equal to, here, the activation energy simply over the constant R. So if I just multiply out the constant R, I can find the activation energy. So that's kind of exciting that that is a number we are able to quantify, even though we weren't necessarily be asked to do that on a test. But why is it important for us? Here's why. Because we want to know what a catalyst is, right? A catalyst is a chemical that helps speed up a reaction without itself being used in the reaction. It appears first on the reactant side in a reaction mechanism and then later on the product side. And it most often helps to improve the sterics of the reaction, right? The orientation of the molecules. It locks the molecules into a positioning that's most beneficial so that when those collisions occur, they will be successful. So it makes the start of the reaction a little bit easier to achieve and to attain. And the last thing I want to do is just go back to these graphs here. If I was to add a catalyst to either one of these reactions, this is how it would change. It would actually lower the activation energy so that it was easier to get that, right? It's easier to roll the ball to the top of the hill, easier to make the spark to get that reaction started. Or in this case, lower the activation energy. And that's kind of how we represent that. So we would just write with a catalyst. This is how the activation energy would change in either an exothermic or an endothermic reaction.